All right, welcome everyone. So tonight we are going to be talking about the history of modern astronomy. And we're sort of defining that as being the history since Galileo, who was the first astronomer to use a telescope. And we'll go all the way from there to the present, to the very recent present, in fact. But before we get started, as always, we need everyone to sign in, please. I will get the link and put it in chat for you to click on in just a second, or you can scan that QR code with your phone there.
Oh, also, guys, please, when you're filling out the questionnaire, please fill out the topics you'd like us to discuss in future meetings so we can use that to make more presentations.
All right, there you go. The link is now in chat for you to fill out the attendance form and sign in. All right, and then once you've done that, we do also have a Discord server. I'm sure you've heard me talk about it enough times already, but it's really fun, so you should join if you already haven't, or if you haven't already. All right, now into some exciting space news from the past week.
Do you want me to talk about it?
Oh yeah, sure.
Yeah.
Yeah, go ahead.
Okay, sure. So on it was Monday, right? I think. Yeah. On Monday, the Royal Astronomical Society announced the discovery of a chemical called phosphine in the atmosphere of Venus. So phosphine gas can be produced in a number of natural ways, and we know that can also be produced by life. So the authors of the paper, they went through all the possible ways that they know phosphine gas can be produced naturally. They were super exhaustive, apparently, and they couldn't think of any possible way that phosphine could be produced on Venus, which could mean a couple of things. It could mean that it's being produced by some unknown chemical process on Venus, which is pretty exciting, or because we know phosphine can be produced by life, the phosphine on Venus could also have been produced by life on Venus, if there is life on Venus. So it could be a sign of life on Venus, possibly. So I mean, we can't say definitively, of course. More studies are going to be done, and we'll probably send probes and things of that nature. But it's a pretty exciting discovery just by itself.
Yeah, this is a huge discovery in astronomy and will definitely have impact on future missions, planning where missions are going to go and which types of missions are going to be funded. And if we find life on Venus, that could be one of the most important discoveries ever. So this is really exciting, even if it's, in no way confirmed yet that there is life on Venus. Also, at next week's presentation, we'll be talking about this more in depth and also about the search for life elsewhere in the solar system, on exoplanets, and everywhere in the universe. So make sure to come back next week if you want to hear more about this discovery in particular and about the search for life everywhere in the universe.
All right, so before we could talk about modern astronomy and basically what we've discovered post 1600s, I just want to catch you all up to speed with what happened starting 3000 BCE up until Galileo. All right, let's go. So, ancient astronomy. We often have this image that ancient astronomy was kind of this mix of actual observations and religion and mythology, and to a very large extent, it is true. There was a heavy focus on timekeeping, calendars, and stars as navigation tools because it was kind of like a necessity of life. You use the stars to navigate your life, your world, and kind of like plan things out. Actually, one of the earliest records of astronomical things is a 32,000-year-old ivory tusk that was carved with a star chart that contained Orion and a couple of other things. An image of a portion of that tusk can actually be shown in the top right corner. There is some debate as to what this was supposed to be exactly, because again, it's kind of hard to decipher these things sometimes, but there is some solid evidence suggesting that it is the earliest known record of a star chart. So again, ancient people were looking up at the stars and questioning and kind of noting these things down from the get-go. Ancient Babylonians around 1800 BCE were actually the first civilization to record repeated cycles of lunar eclipses, and they kept very detailed records of celestial bodies because it proved to be a very important part of their culture and just their record keeping in general. We've also noted astronomical events throughout history overall. Chinese astronomers in particular have been very well known for keeping detailed records of celestial occurrences, and they would often record these very unique features as guest stars. So in 1504, not 1504, wow. In the year 1054, Chinese astronomers were able to record a supernova event, which we know as a very catastrophic event of a star's death. And this particular supernova actually was the thing that created the Crab Nebula. And ancient astronomers were able to record this as something that was 4 times as bright as what Venus appeared to be and was visible even in daylight for 23 days. And the bottom right picture is actually a very primitive drawing or like marking of that actual event. And we actually have physical records proving this. So again, we've known throughout history the importance of astronomy. We kind of like noted these things down over time. Next slide. And it wasn't just the ancient Babylonians or the ancient Chinese civilizations that focused on astronomy. One of the most famous groups that worked on astronomical observations were the ancient Greeks. And they focused a lot of their theories on observations on more rational physical explanations of the heavens. So they made a bunch of calculations about parallax, which is the observed apparent changes of an object that are caused by just changes of a position of the actual observer. And an image of that can be shown in the top right, where the Earth during a certain time of the year is positioned in a certain place in its orbit, and a couple of months later it's going to be in a different spot, and because of that, different objects will appear to have different locations, and using those angles and some geometry, we could figure out different properties or the different basic calculations of what that object is. And ancient Greeks also made detailed records of stellar magnitudes and other basic celestial geometries, which proved to be very handy. There was also a little subsection of ancient Greek astronomy, which is known as Hellenistic astronomy, that is mostly focused on when the Greeks conquered ancient Egypt, and they were able to fuse a lot of Egyptian focus of astronomy with their knowledge from the ancient Greeks. And there was also a very heavy emphasis of mathematical explanation and deriving theories at the Library of Alexandria, which is kind of considered like the big hub of information of that time period in the late BCE period. One of the most important ones was Eratosthenes, who was a Hellenistic astronomer and mathematician who very accurately calculated the circumference of the Earth. He actually came within about 1,000 miles of what the actual distance is, and that's thousands of years ago. So again, a very interesting discovery and very interesting calculation done with very crude instruments. I believe his entire experiment was based upon just measuring different shadows and how they kind of played together, and measuring and calculating that and using basic geometry just figure out the circumference of the Earth. Ancient Arabia also had very interesting astronomy. They focused on geometric models, and they gave non-heliocentric and geocentric alternatives to solar system models, which contrasted what was happening in the more Western astronomical world. And you also have Mayan civilizations who focused a lot on calendars and physical observations using ancient observatories. And one of these observatories is actually on the bottom right, which is known as El Caracol. It's a line for different solstices, and is actually believed that most of their observatories were kind of following, or they were kind of laid out so they followed Venus's orbit, since it was a very interesting object to them. I'm not sure exactly why that reason is, but this observatory in particular was kind of aligned to follow Venus's path through the sky. Next slide. Okay, So, and a very important part of ancient astronomy and just astronomy as it leads into the 1600s was the Copernican and the scientific revolution. So up until the mid 1500s, the most prevalent model for the solar system was the geocentric model, which said that the Earth was the center of the solar system and all the planets and the sun revolved around it. In 1543, Copernicus put forth his theory in his paper or book known as the On the Revolutions, and it put forth the heliocentric model. And the heliocentric model was proposed at different points in time before too, but this was the first time it was like officially put forth in a very strong manner, and it actually did have support by one other mathematician slash cosmologist known as Giordano Bruno, and Bruno actually came up with a lot of interesting theories along with this, which included that stars are distant suns that each have their own planets and each planet have their own planetary systems, and sometimes these planets might even have the capacity to support and foster life, which is a very interesting concept, especially for something so far long ago in time. He also proposed that the universe is infinite and it has no center. And these theories were something that kind of occurred throughout different civilizations too, but it was kind of the first time that such theories kind of found a really prevalent voice in the scientific communities. Next slide. All right, so some of the instruments used by ancient astronomers, we tend to think that they just kind of stared up, but they actually had some very interesting tools to help them with their measurements. Many of the older civilizations, especially like in ancient Greece or ancient Babylonia, they used specific structures of stones that were laid out in the ground to kind of act as sundials or calendars to follow the paths of different objects in the sky. You also have the armillary sphere, which models different celestial objects and spheres along different celestial lines and latitudes. It was actually used by a bunch of different civilizations. It was used in both Western astronomy and Chinese, Indian, various ones. You also have the astrolabe, which is on the right. It was heavily used during the Islamic Golden Age to make very like crude calculations for different celestial bodies, and was mainly used for navigational purposes. But the one I kind of want to focus on is the instrument that ancient Greeks used. I'm going to really butcher the pronunciation. I think it's called Antikythera. It's actually a hand-powered analog computer that's used to predict eclipses and orbits, and it was used between 80 and 200 BCE. So if you go to the next slide, there's actually a quick video explaining how it basically works. Yeah, that should be enough.
Yeah, that's really cool. How old was that, Ashita?
It was mainly used from like 80 to 200 BCE.
That's crazy.
I know, right? Absolutely insane.
All right, so I'm going to talk to you guys about this 200-year span here between 16 and 1800. So a couple really cool discoveries that happened during this time. So we're going to start with Kepler's laws of planetary motion, and this was published in 1609. And he had 3 laws describing the motion of the planets as they move around the sun. So the first one is that the orbit of a planet is an ellipse with the sun at one of the 2 foci. And you can see that in the picture on the bottom right, that the sun is, it's an ellipse, it's not a circle, and the sun is on the left-hand side of it. The second law is that a line segment joining a planet and the sun sweeps out across equal area during intervals of time. And the third one is the square of a planet's orbital period is proportional to the cube of the semi-major of its orbit. Now, what does that mean? Because that's confusing even for me. So the second law is showing that the objects are going to move faster depending on where they are in their orbit. So you can see in the blue section, is a smaller amount of time for a month, or I'm sorry, is a larger distance for a month on the left side than it is on the right side. And the third law shows that it's proportional. How long an object takes to orbit the sun is proportional to its distance away from the sun. And there's a bunch of math proving that, but showed that it's a constant, and you can calculate it for all the objects in the solar system. So that was some pretty innovative stuff, especially for the time. And these discoveries improved on the model of Copernicus, which Ashita talked about earlier, and helped to further prove that this heliocentric point of view. Next slide. So another big discovery of the era is the telescope. The first patent of the telescope dates back to 1608. It was by a man named Hans Lippershey from the Netherlands. So it wasn't actually Galileo who created the first telescope, but he did make some really drastic improvements on it. And his design, which we see on this picture, in this picture on the right here, was made a year later, and he had a telescope with a 3 times magnification, and later on he also added up to 30 times magnification. So some really good viewing was able to be gotten from that. Galileo was also the first person to use a telescope for astronomical observations. And he made some really important observations about Jupiter a year after this in 1610, which we'll talk about in the next slide. So Jupiter's moons. Galileo, using his new telescope, was able to discover the 4 moons of Jupiter. We now know them as the Galilean moons, Europa, Io, Callisto, and Ganymede. This is really important, and I'll explain why, because these observations, fully confirm the Copernican heliocentric theory that the sun is at the center of our solar system. So the picture we see on the right here is, about a 2-week span of his nightly observations of Jupiter through his telescope. And, the larger of the circles on each of the line is Jupiter, and the smaller ones that are stars are the moons. And he thought at first that they were stars that were just really close to Jupiter, but then noticed that they moved, and in very odd ways that the stars shouldn't have been moving. So he was able to see them all throughout this time, and this confirmed to him and for the scientific community that these were actually objects that were orbiting Jupiter, which then really helped to prove that these things weren't all orbiting the Earth. So that was a really important discovery by Galileo there. Okay, so a couple other observations that Galileo made, not as important as the Jupiter one, but still pretty interesting. He was able to see that Venus goes through a full set of phases similar to the moon, and that's in the picture on the bottom left there. So we can actually see different phases of Venus, which also helps to show that that stuff is going around the sun. He observed Saturn, and initially mistook the rings as being other bodies near it. So that's the picture on the right. He originally thought it was like a tri-system with 3 objects in the area, because again, this telescope was still pretty primitive. Even it was great for the time, but nothing what we have like what we have today. And he also discovered that the moon was not a smooth sphere. Up until that time, it was pretty accepted that the moon was just pretty smooth. But he was able to use his telescope to look at it and saw craters and saw mountains all across its surface. All right, Isaac Newton. So instead of doing a discovery, I'm just going to talk about the person because of the sheer quantity of things that this person did. He was one of the most influential scientists of all time, a key figure in the scientific revolution. One of his major discoveries was the law of universal gravitation, describes how gravity works to an extraordinary degree of accuracy. So he was able to figure out how all the particles are attracted to each other and, form and controlled by gravity. He also had the laws of motion that he published in his book, Principia, in 1687. And his three laws of motion pretty much, object will stay at rest if it's in rest, it stays in motion if it's in motion. He was able to figure out how acceleration works on an object, that it's directly related to the magnitude of the force, the direction of the force, so that if you put the same force on two different objects that have two different weights, it's going to affect them differently. And then the ever famous, every action has a equal and opposite reaction. And he's also credited with, one of the inventors of calculus, which is why I don't like him very much. So, all right, next slide. Next slide. There we go. So some other, okay. So the Messier catalog, which was a group of astronomical objects that were cataloged by Charles Messier. So he was out looking at the sky trying to find comets. So he wasn't really interested in the other objects that he saw, but he did still, put them in a catalog because he did find them. And he didn't really know what they were, but we now know they were, a whole wide range of deep sky objects from, star clusters, nebulae, galaxies. And we still use this list today, and has 110 items on it. And that's what the picture on the bottom right is, all the items, from the Crab Nebula to all the different galaxies and whatnot, and also including the Pleiades, which is in the top right. That's M45. I put it there because that's my favorite deep sky object. But yeah, he was able to catalog all this, and unbeknownst to him, it turned out to be very important and stuff that we still use today. And lastly, just a couple other notable discoveries of this era. There was a supernova in 1604 in the constellation of Ficus. That was the last time we had a supernova in the Milky Way. There was one later on that took place in, I believe it was the Large Magellanic Cloud, but it doesn't really count. It's our satellite galaxy. So that was really cool. And a couple of these people that we talked about were able to observe this supernova. In 1655, Christian Huygens studied Saturn, discovered its largest moon, Titan. 50 years later, Edmund Halley predicts the return of a comet in 1758. This is correct, and then they named that, Halley's Comet. 50 years after that, we have Nicolas de la Ciele, I don't know how to pronounce that, travels to the southern hemisphere, and he starts compiling a catalog of over 10,000 stars, which is definitely very helpful. And last but not least, in 1781, William Herschel discovers Uranus. He first mistook it to be a comet, but we obviously now know that that is the seventh planet.
All right, so now on to our next time period. We're moving into the 19th century, 1800s. So one of the earliest and probably one of the most important discoveries from the 19th century was made by Fraunhofer. The sun spectrum has been known to, contain all the colors since earlier. Newton was the first one to use a prism to split the sun spectrum and observe that white light was made up of all the different colors. But then later on, a guy named Wollaston was the first to notice something interesting within that spectrum, is that it wasn't a continuous spectrum of all the colors. There were a few little gaps missing, some black lines in between the colors. And he didn't really understand what these were at the time. He wrote about them, he noted where they were in the spectrum, but he thought they might just be natural boundaries between the colors or something like that, which, doesn't sound like it makes sense today, but at the time they didn't really know how light worked. So it seemed like a good guess that there might just be boundaries between the different colors, that there was a natural gap between this wavelength of blue and that wavelength of blue, where it became a different color or something like that. But Fraunhofer was the first one to figure out that these lines actually meant something. And he was the first one to build a spectroscope using a diffraction grating instead of just a prism. And that allowed him to get a lot more resolution, to see exactly where all of the lines were, see some more faint lines that Wollaston wasn't able to observe. And it allowed him to accurately and repeatedly observe these spectral lines. And we'll come back to spectroscopy a little later in the 1800s. But Fraunhofer was the first one to figure out that these lines exist. And he also observed spectral lines of some other things by burning salts and things like that. They make all those cool colored flames. You might have done that in chemistry class. And he saw that lots of different things created these spectral emission lines and absorption lines. All right, so now the first accurate parallax measurement was performed in 1838. So before telling you exactly how that was done, I'm going to say a little bit about what parallax is and why it's useful for anyone who doesn't know. So parallax is a way of measuring distance in space. Because here on Earth, obviously, if you want to figure out the distance, you can just take some object of a known distance, whether that's a meter stick or whether that's your stride length, and you can use that to just physically measure out the distance between two things. But in space, obviously, for a very long time, we couldn't physically go anywhere. So we had to figure out how far away things were just by looking at them. And parallax is one way to do that. So you can see down here at the bottom, there's sort of a simplistic model of the solar system here with the sun in the middle, and you can see the Earth going around its orbit. So the Earth's orbit, or the Earth's position in space changes throughout the year as it goes through its orbit. So if you take a background star, like this one here, and you look at it, say in July, you can see that there's a certain angle between the sun and that star. And if you can measure that very precisely, and then when the Earth is on the other side of its orbit 6 months later in February, and you take the same measurement, you can figure out what that angle is there. And then, you know, with some simple trigonometry, you can figure out how far away that star is using that angle and using the distance to the sun, which had already been calculated. So the first star this was done for was a star called 61 Cygni. And that one was chosen because it had been observed to have a high amount of proper motion, which means its movement relative to fixed background stars. So all stars have some amount of proper motion, but the further away those stars are, the less they move relative to each other. So you can see in the bottom right here, this is a modern image of 61 Cygni, and you can see it moving noticeably against those background stars. At the time, they didn't have pictures this good, but they were able to tell with observations through telescopes that 61 Cygni was moving relative to those background stars, which made them think it was probably one of the closest stars to Earth, and they were right about that. It's not the closest one, but it was one of the closest that they could see at the time and measure the proper motion of. So a bunch of astronomers tried to measure the parallax of this early on in the 1800s, around 1812, but the instruments at the time didn't really have enough precision, and astronomers were getting wildly different results, and some were saying that they didn't measure any parallax at all, so they kind of gave up on that for a while. But later on in 1838, Friedrich Bessel made the first accurate measurement of the parallax of 61 Cygni. And he used that with a device called a heliometer, which had actually also been created by Fraunhofer, who observed those spectral lines. And Bessel estimated a distance of 10.4 light years in modern units to 61 Cygni, which is pretty close to the actual distance we have today of about 11.4 light years. So he was only off by about 10%, which is pretty good for the primitive nature of the instruments at the time. All right, Neptune, I think, was the last planet to be discovered, right? And that was in 1846, not counting Pluto, which is a dwarf planet now. But Neptune was the last planet that's still considered a planet to be discovered. And the way Neptune was discovered was actually pretty interesting. Galileo was actually the first person to observe Neptune, but at the time he just thought it was a star because it doesn't have a lot of proper motion. And it actually turns out that just by coincidence, at the time he observed it, it was at the time that Earth was passing Neptune in its orbit. So it was when Neptune would be changing from prograde to retrograde motion in the sky. So changing from moving in one direction to the other. So it sort of had this slowest amount of motion in the sky at that time. So just by coincidence, Galileo happened to be really unlucky and look at Neptune at the time that it was moving least in the sky. So at the time, no one figured out that it was a planet. They just thought it was a background star. But later on, Alexis Bouvard, using Kepler's laws and Newton's equations, tried to predict the orbit of Uranus, which had already been discovered. And he figured out with some observations with the telescope that the actual orbit of Uranus wasn't matching up with his mathematical predictions. And he went back and he double-checked his predictions, and other people made the same mathematical predictions, and none of theirs were matching up with the observed orbit of Uranus. So Alexis Bouvard postulated that there must be some large planet near the orbit of Uranus that was impacting its orbit slightly. And two men, John Couch Adams and Urbain Le Verrier, both attempted to predict where that planet would be, how big it was, what its orbit was like, based on his calculations and the observed orbit. And Le Verrier wrote a letter to an astronomer at the Berlin Observatory, Johann Galle, and asked him to search a specific region of the sky to check if his observations were correct and to check if Neptune was actually there. And Galle did this and found on the first night, he observed it right away. He went to the spot that Le Verrier predicted, and within 1 degree of the predicted position, he found Neptune. And he kept observing over a couple nights to make sure to see if it was moving relative to the background stars, and it was. So Neptune was actually sort of mathematically discovered first, and then observationally discovered later based on those mathematical predictions, which is really cool. All right, so now back to spectroscopy. So now spectroscopy had been around for a while. Fraunhofer's diffraction grating spectrometer had been around for a while. And two scientists, Kirchhoff and Bunsen, who is famous for the Bunsen burner, which you probably also used in a chemistry class, worked to catalog the spectral lines of a bunch of different known chemicals and chemical elements. And they figured out that each element has its own unique set of spectral lines. And they published their first findings in 1860. They had measured the spectra of 8 elements so far, and they had demonstrated that spectroscopy could be used to determine what elements were in an unknown sample. And that's important both in lab work and in astronomy, because now you can determine what the elemental makeup of something is without having to perform direct chemical analysis of it. And spectroscopy was actually used in 1868 to discover helium. Helium was actually not discovered on Earth. It was first discovered in the atmosphere of the sun, which is why it's named helium. It's named after the Greek god Helios, which is the god of the sun. So helium was first observed as a spectral line in the atmosphere of the sun, and it didn't match up with any known spectral line on Earth. And then about 30 years later, scientists on Earth finally found helium gas. I think it was originally found in a sample of uranium, and matched it up with the emission line observed in the sun and figured out what this element was. All right, so some other notable achievements from the 1800s. A bunch of large telescopes were built. The one you can see on the right there was the largest refracting telescope ever built, and that's to date. There still hasn't been a larger refracting telescope built since then, because since then we've mainly focused on building large reflecting telescopes, because those are easier to make at a large scale because they don't have to be quite as long, so they're not as unwieldy and hard to make. But some other major discoveries, the first astrophotograph was taken in 1839 using a daguerreotype. It was a picture of the moon. It didn't turn out very well because the tracking on the telescope wasn't set up properly, so the moon ended up being a blurry smudge across the picture as it moved through the sky, but that was the first ever photograph taken through a telescope. Another large telescope built in Ireland, a 1.83 meter telescope, and that was the largest diameter telescope for a long time, until about 1917. Stefan and Boltzmann in the 1880s derived the relationship between the temperature and the power radiated by a star. That's the Stefan-Boltzmann law. And in 1895, the Russian Konstantin Tsiolkovsky figured out that rockets could work in a vacuum, and he was the first to theorize those as a future method of space travel because they would work without the need for air and oxygen.
All right, sweet. So now we're in the era of 1900 to 1960. So I'm going to start with something that kind of overlaps with the previous era, but also happened mostly in like the first part of the 20th century. So next slide, please. So the Harvard Observatory, I know how words work. The Harvard Observatory computers were this group of women who worked in the Harvard Observatory, like starting in 1881 and up through the 1950s. And what was happening was around this time, we were starting to figure out how to make daguerreotypes. So Henry mentioned that the first image ever taken through a telescope was a daguerreotype of the moon. We got better and better and better at taking pictures through telescopes, and we would put them on photographic plates. So you can see here this picture on the right with the magnifying glass here, that is a photographic plate. And the style of these was that you could like put a spectroscopy, whatever the instrument is that you do spectroscopy with. Sorry, losing words a little bit tonight. And you can get a spectrograph from those points, which is super cool. And it means that you don't have to point your prism at the star to get the diffraction pattern. So this means that there's now a ton of data to process, because look at all of the stars that are on this image on the right, and imagine doing a spectrograph for every one of them. So lots and lots and lots of data to process. So the Harvard College Observatory hired a bunch of computers. Now, computers were people whose job it was to take data off of those things and catalog it. And it started hiring women. So the first one's name was Selena Bond, and then the next one was named Williamina Fleming. Williamina Fleming actually happened to be a maid in the household of the guy who was running the observatory, but like she was just amazing with math, and Edward Pickering, who was running the observatory, was like, hey, do you want to work here? And she was like, yeah. So, and then by 1920, there were 40 of these computers working there. And then as these computers started to like catalog things more and more, they started to make their own discoveries. So we have Williamina Fleming discovered the first white dwarf. We have Antonia C. Maury. She took the Draper catalog, which was the original way that we had categorized stars, and just made it a lot more detailed and had a lot more categories. And then Annie Jump Cannon took that system and made it into the OBA FGKM system that we have now, based on Balmer lines, which are a kind of absorption line that shows up in hydrogen spectroscopy. And we have Henrietta Swan-Leavitt. She figured out the law for Cepheid distance, which was super important for Hubble figuring out the expansion of the universe. And then we have Cecilia Payne-Gaposchkin, whose PhD thesis showed that the sun's composition is not Earth-like, but is in fact mostly hydrogen with some helium. It's considered the most brilliant PhD thesis of all time. So here on the bottom right, you can see this is a group of some of the computers standing with Edward Pickering in the back. I wish I knew who was in this picture and which, like, I wish I knew their names, but I don't. But this is super cool. So I read this in a book called The Glass Universe. It's super cool, highly recommend. Yeah. Oh, and in my background, this is the Harvard University Observatory. It's this dome right here. They had this giant telescope called the Great Refractor. So that's the Harvard Observatory computers. Next slide, please. Sweet. So now we're in 1905 and 1915, and we're starting to have the sort of advent of modern physics. So kind of the first thing that happens in 1905 is Einstein comes out with special relativity. And how special relativity works is it deals with things that are near the speed of light, and we would call them relativistic. And it's founded on these like two sort of postulates. The first is that the speed of light is constant in all reference frames. So if I am on a train that is heading east and then Perry is on a train that is heading west, we're both going to measure the speed of light to be the same regardless of how fast we're going or what direction we're going in. And the second postulate is that physics works the same regardless of what reference frame you're in. Which would, you know, these two things would seem to make sense, right? Like this feels like common sense, but it ends up with things sort of distort to fit the speed of light. So you have length contraction and time dilation. Space and time change to make sure that the speed of light is constant, which is super cool. And this was super important for when we started looking at things that were traveling near, like at a larger fraction of the speed of light. And of course, astronomy deals with, like, almost all of our information about the universe comes in the form of light. So it's super important that we understand how it works. And then we had general relativity in 1915, which is, if you've ever seen this image on the bottom left here of you have space-time is like fabric and then mass curves that's where that comes from. So it's the idea that gravity is just sort of the curvature of space-time was the idea. And this has been confirmed, well, things that are predicted by this model have been confirmed by LIGO. So this model predicted gravitational waves, which were then confirmed at LIGO. And it also helped us correct an error in Mercury's orbit that we hadn't really been able to explain. So how did this impact astronomy? Like I said before, light and nuclear physics are two hugely important things to the field of astronomy, because nuclear physics is basically how we know anything that we know about what happens on the inside of a star. And light is how we get information on basically everything, because we can't perform any experiments. So next slide, please. Thank you. So then the next discovery that's a really big deal is the discovery of that the universe is expanding. So in 1912, we have the discovery that distant galaxies are moving away from us. They are redshifted. And then in 1922, we sort of have somebody take the general relativity field equations for gravity and do the theory to show that, yeah, this agrees, things should be moving away from us. And then in 1927, we have the first direct observational evidence that the space seems to be expanding. So to kind of illustrate what this means, there's this example I really like of a raisin loaf. So how it works is, if you see this picture on the right here, you have this sort of loaf of bread with raisins in it. They're like a centimeter away. And then you put this loaf in the oven and the bread expands. So the bread expanding is kind of like our universe expanding. And now these raisins are each 3 centimeters apart. But if I look at this local raisin right here, I started 1 centimeter away from raisin 1, 2 centimeters away from raisin 2, and 3 centimeters away from raisin 3. Now I'm 3 centimeters away from raisin 1, 6 centimeters away from raisin 2, and 9 centimeters away from raisin 3. So that's what we mean when space itself is expanding, the distances between things are getting larger. So this is super important for cosmology in particular, but also every other field of astronomy. So even though this was kind of a physics discovery, kind of an astronomy discovery, it was super important to astronomical history. So next slide, please. Thank you. And then in the 40s, we have a development that is, I think, probably the most influential to how we do modern astronomy. And that's the first stored program computer developed in the 40s. So how this sort of came about is that World War II created a need for a large volume of really high-speed computations. So that was everything from the Manhattan Project needed to be able to run really rudimentary mathematical simulations to try and figure out how to make an atom bomb. And then the other sort of side of this is that in England, they're trying to run cryptography, a cryptography effort to try and break the Germans' Enigma code. And it's a really complicated system, and it needs lots and lots of computations, and it needs to happen really quickly. So you can't really do this with human computers, in particular because lots of people were going off to war, so your supply of human computers was dwindling. So there was the Harvard Mark I that was used for the Manhattan Project, which was the nuclear bomb. And how that one worked was it worked on punch cards, which was you have this long string of tape and you punch holes in it, and that tells the computer, that'll give the computer commands. but it had like no memory or storage. So every time you wanted to run a program, you would have to take the same set of punch cards, put them all through the computer, and like flip a bunch of switches to input like numbers that you wanted that program to deal with. And it was, just to give you some context for how this computer worked, if you wanted to multiply two numbers together, it took 3 seconds. If you wanted to divide two numbers, it would take 15. And if you wanted to take the logarithm of a number, it would take many minutes. Now, if I take my scientific calculator and plug in, you know, like log of 10, I'm gonna get an answer in like a matter of milliseconds. So we've come a long way, but this was sort of the very beginning part of our computing history. And so that was the Harvard Mark I. And then there was the computer known as the bomb. I think it's just bomb, that was used at Bletchley Park, which was in England for the code breaking. And this is Alan Turing in the lower right-hand corner. He developed this bomb, and this is sort of the precursor to his Turing machine, which is what we just call a computer now. The idea that you don't have to build a specific machine to do specific kinds of calculations. So his sort of theory was that you can make a machine that can run any type of calculation, which is what our modern computers are. So this led to a revolution in how we think about computer science. And this is super relevant to astronomy because every astronomer that I know, not that I know that many astronomers, every astrophysics sort of field of research that I know is now using computers to do calculations or even to run simulations. And the Turing machine is really good for complex algorithms, which are really super important. So that was the 1900s to the 1960s.
Okay, so I'll be talking from the 1960s up until the present day. So if you want to go to the next slide. Right, so the first thing we'll be talking about is the discovery of the first exoplanet in 1992. So exoplanets are planets that orbit a star that isn't our sun. And like we mentioned earlier in the presentation, they were speculated to exist for centuries, but actually detecting one was super duper difficult. So the first two exoplanets that were detected were actually detected around a pulsar, PSR B1257 plus 12. So a pulsar is pretty much a super compact star. It's about the size of Manhattan, but about the same mass as the mass of the sun. And neutron stars can rotate really quickly, and sometimes they have super powerful beams shooting out of their axis of shooting out of them. And what can happen is that by chance, as that beam might line up with Earth, and as the neutron star rotates, that beam would hit the Earth, and then it would go away, and then it would hit the Earth again, and then it would go away because the neutron star is rotating. And we can measure the time between those pulses. So normally pulsars are, the time between the pulses from a pulsar are super duper regular. Like, it's probably the most regular thing that we know of in the universe. However, scientists looked at the time between the pulses from this pulsar, and they noticed that it wasn't constant, it varied actually. So in the bottom right is actually a plot from the discovery paper. So on the y-axis is the time between the pulses, and on the x-axis is just time, see 1990, the year 1990, then towards the end of 1991 on the end. And if the time between the pulses remained constant, you would expect to just see a constant horizontal line. But you don't. The data points are the black points over here, and you can see that there's some over here and some over there. I keep forgetting you can't see my mouse, but anyway, they're not on a straight line. Anyway, yeah, and they did math and they did some simulations, and they worked out that if you have two planets of such and such mass and such period orbiting around the pulsar, then it would actually give you this pulsar, the time between the pulses period that we see. And the solid black line on the bottom right plot is what they computed it would be for these two planets. And as you can see, it fits the data pretty darn well. And interestingly, both of the planets that they discovered were around 4 Earth masses, which is actually really small for exoplanets, relatively speaking, that we saw. And they have periods of about 66 and 98 days, respectively. So you can go on to the next slide. So the next thing is that's equally important is the first exoplanet discovered around a sun-like star. So as you may recall on the last slide, I mentioned that the exoplanets were found around a pulsar, and a pulsar is not at all like our sun. So it could have just been that it was kind of like a one-off, occurrence. It was not regular at all. But finding the first exoplanet around a sun-like star really showed that it was more regular in the universe, and that there's, that the Earth isn't unique, I suppose. So the first exoplanet that was discovered around a sun-like star was discovered in 1995, and it was discovered around the star 51 Pegasi, and it was discovered using the radial velocity technique. And what that basically involves is they measured the movement of 51 Pegasi using Doppler shifting of the spectral lines. Now, there's actually a video on the next slide, if you can go there and play that. Yeah, so what you can see here is when you have a planet orbiting around the sun, around a star, it causes the star to kind of wobble or move. And sometimes it's moving away from us, and sometimes it's moving closer to us. And as it's moving away from us, the spectral lines that it emits are going to be redshifted. And as it moves closer to us, the spectral lines that it emits are going to be blue shifted. And by measuring how much the spectral lines are blue shifted and red shifted, we can calculate how quickly the star is moving. And from that, we can do some math and in fact find out some characteristics of the planet that orbits it. If you want to go back to the last slide, actually. Yeah, thanks. So that's pretty much what they did with 51 Pegasi. If you look in the, can you make the presentation full screen, please? Thanks. So if you look in the bottom right, this is actually a plot from their discovery paper. And on the y-axis, it's pretty much the speed of the star that they measured. You can see there's a little dotted line going at 0, and that's pretty much where the star isn't moving away from us or towards us. So it stays the same distance. Above the dotted line is moving away from us, and below the dotted line is moving toward us. And the black lines are their data. And as you can see, it kind of goes away from us, and then it comes closer to us, and then it goes away from us pretty regularly. And using that, they were able to find out that there's a planet going around the star 51 Pegasi. And they found that that planet has around a mass of about 0.4 times the mass of Jupiter. It has a period of around 4 days, which basically means that it's orbiting super duper close to the star. So that did a few things. Like I mentioned, that confirmed that sun-like stars can host exoplanets. That our solar system isn't unique in the universe. But its properties weren't consistent with solar system formation theories at the time, because as you may recall from last meeting, if you were there, we kind of discussed how we thought that gas giants can only form farther out in the star system, and that terrestrial planets have to form closer in. You can't really have gas giants super close to the star, but that's exactly what we saw here. So that kind of so the existence of a gas giant so close to the star kind of threw a wrench in our formation theories. And this was actually so important that it shared the 2019 Nobel Prize in Physics last year. If you want to go to the next slide. Yeah, or the one after that. Yeah. Next, we'll talk about dark energy. So dark energy was pretty much discovered in 1998. So as we mentioned earlier, we found evidence that the universe is expanding way back in the early 20th century. However, the general feeling was that that acceleration, that expansion was actually slowing down because of gravity. Gravity would work against that expansion, kind of pull space closer together and slow down the expansion. But in 1998, we saw that the expansion of the universe is actually accelerating. And this discovery was so important, it actually won the 2011 Nobel Prize in Physics. So because the expansion of the universe is accelerating, and we would expect it to be slowing down because of gravity, there needed to be some sort of force or something that would counteract gravity and force the expansion to accelerate. And that's exactly what dark energy is. But we have no idea what dark energy actually is, other than the fact that it speeds up the expansion of that it accelerates the expansion of the universe. So it's a major mystery what dark energy actually is at its core. But we do know that it makes up 72% of the total energy content in the universe. So it's the vast majority of the energy in the universe, and we have no idea what it is. So we're working on that. If you want to go to the next slide. And now we'll talk a bit about dark matter. So there's a general belief or thought sometimes that dark matter and dark energy are similar, and they're really not at all, other than the fact that they both have dark in their names. So dark matter has a long history that begins in the 1930s, but most of it actually is happened in the 70s. So I'll go through its history. So in 1933, Fritz Zwicky discovered that galaxies in the Gamma cluster, which is a cluster of galaxies, are moving too fast based on the mass that we can see. So what happens when you have a cluster of galaxies is you have galaxies that are held together gravitationally, and they're kind of just moving around each other because of gravity. And using physics, you can calculate how fast they should be moving based on how much mass is in the galaxy cluster. And Zwicky saw that they were moving way too fast based on the mass that he could see. And he suggested the existence of something he called dark matter. So moving on a bit 40 years down the line, Vera Rubin and others measured the rotation curves of galaxies in detail. And their work suggested more need for dark matter. So what they did specifically is, let's first describe what rotation curves, I suppose, are. So if you look at a galaxy, you can measure how fast stars are orbiting the center of that galaxy. So if you plot how fast the star is going, how fast it's orbiting the center of that galaxy as a function of how far away from the center it is, you would expect it to follow a certain line, or a certain function, which you can calculate using physics. And actually, if you look in the bottom right, you can actually see what the rotation curve for the Andromeda galaxy is. Velocity, kilometers per second, is on the y-axis, and the distance from the center of the galaxy is on the x-axis. And there's this dotted line, or this dashed line, I guess, which is what you would expect to see. That's not what we see. You actually see that as stars move farther away from the center of the galaxy, how fast they're going around the center of the galaxy actually speeds up, which isn't what you would expect at all if you only had, visible, if the only matter that was there was matter that you could see. So naturally that implied that there's matter there that you can't see, and that's what dark matter would be. And as time went on, in the 1980s, we had even more evidence for dark matter that just came pouring in. Mass measurements from gravitational lensing, which I'll mention on the next slide, and also patterns in the cosmic microwave background, which I'll also mention on the next slide, also pointed towards dark matter. If you want to go to the next slide real quick. Yeah, so in the top right, you can see a description of what gravitational lensing is. So gravity can actually bend light. So if you have a distant galaxy, like in this image, you have a distant galaxy, you have light that's coming to us, and in between there's a massive galaxy cluster or something massive. That galaxy cluster would bend the light that's coming toward us. And based on how much that light is bent, you could directly measure how much mass is in that galaxy cluster that's between the galaxy that we're seeing and the galaxy and us. And we can compare that mass that we observe from gravitational lensing with the mass that we expect to see based on just from the light. And again, there's way more matter than we expect there to be. And in the bottom left, there's an image of the cosmic microwave background, which is pretty much the leftover light from the creation of the universe. And as you can see, there's some different spots. It's not completely uniform, and there's some patterns you can actually find if you look for it. And if you do some super complex physics, you would actually see that the patterns that we see in the CMB is consistent with what we would expect from dark matter. And then in 2006, we had the X-ray image of the bullet cluster, which was released. That's in the bottom right. So the bullet cluster is pretty much two galaxies that collided. And using a combination of gravitational lensing and X-ray imaging, you can measure the mass distribution in the galaxies as well as where the gas is. So if you actually look in the bottom right in that image, you'll see two kind of lobes, one on the left and one on the right, and that's from the two galaxies that collided. They kind of went past each other. Yeah, so you'll see actually that there's most of the gas actually kind of stayed in the center, because the gases from one galaxy and the gas from the other slowed each other down through friction, and they mostly stayed in the center. But in the blue actually is where most of the matter is, which is why it's labeled DM for dark matter. And we can see clearly that the gas, which is where most of the visible mass is, isn't where most of the actual mass is. So you can clearly see pretty definitively that dark matter is separate from visible matter. So you take all this into account, there's a huge amount of evidence for dark matter. We don't know what it is, but we know that there's about 6 times more dark matter than visible matter in the universe. So that's an active area of research. If you want to keep going. Right, another major thing that happened recently, gravitational waves were detected in 2016. So they were theorized to exist from Einstein's theory of general relativity, and the general idea is that when two massive bodies orbit each other, they release gravitational waves. And I have some videos of that on the next slide, which we can get to in a second. And they were detected by LIGO using laser interferometry. So on the bottom right, you can actually see an image of LIGO, and it basically consists of two giant laser beams, about 4 kilometers in length, as you can see each arm, with a mirror at the end. And what happens is they shoot a laser from the center, and it goes to the end. There's a mirror there, and then it comes back, and it just keeps bouncing around in that tube a bunch of times, and also in the tube that's going to the right. And eventually they're recombined. And so a more simplified image of what happens with the lasers is in the top right. You have a laser. There's a beam splitter which splits the laser in half. Half of it goes to a mirror going up. The other half keeps going straight, goes to another mirror. And what happens is eventually those two laser lights are recombined. And then you can detect that recombined laser. And the thing is if the distance between, if the distance of one arm or the distance of the other arm, if that changes, you can detect that in the combined beam. And using that fact, LIGO was able to detect a change in the distance between the arms of about 1/10,000th the width of a proton, which is super precise. And using that, they were able to help validate GR by detecting gravitational waves. And it also opened up a completely new way to study space. So, and also, I forgot to mention that the reason this works is because gravitational waves actually, they bend space, and they actually change distances, which is why we'd want to detect a change in, the different, which way we want to detect the a change in the length of one arm from the other. If you want to go to the next slide. Right, so first let's play the video on the left. So like I said, so this is a video of two black holes that are orbiting each other, and you can kind of see that they're releasing gravitational waves, where the different shades of green is like the different amounts of stretching and contracting of the fabric of space-time. And as you can see, they orbit closer and closer to each other. The gravitational waves get more intense until eventually there's a big chirp, is what they call it, and then it calms down. Now, if you want to play the video on the right, actually. So about in Astrofest, which we mentioned before, about 2 years ago, we had a demonstration of this, and we basically took a drill and we stuck it on top of a wood block, and on that wood block, there were two little like wheels on each end. And then we spun that over a certain fabric called lycra. And as you can see, as we spun those two wheels, it kind of created, you can kind of see gravitational waves, or the analog of them in the lycra, which is pretty neat. So you can go on to the next slide now. Right, another major thing, getting closer to the present day, the first photo of a black hole. So black holes are predicted by general relativity, and there was a whole bunch of evidence for black holes prior to getting this black hole photo, but this was like the first definitive, evidence that black holes actually existed. So this was taken by the Event Horizon Telescope using interferometry. So what they did was they used many telescopes around the world, which you can see in the bottom right, and they combined their data to approximate a telescope that had the size of the Earth, because the black hole, even though it's huge, relatively speaking, in the night sky, it's really small in the night sky, so you need a huge resolution to view it. So the black hole they took a photo of was the black hole at the center of Messier 87. And that black hole had a mass of about 6.5 billion solar masses, and the radius of that black hole is about 122 AU, where 1 AU is the distance between the sun and the Earth. So it's a pretty massive black hole, which is one of the reasons we were able to photograph it. Yeah, the image may look a bit blurry, but if you look in the bottom left, actually, you can see a simulation of a black hole, and also right next to it, under the caption EHT reconstruction, you can see how they would reconstruct that image, and it looks somewhat similar to the image that we got. So if we had completely perfect resolution, we would see the image on the bottom left under the simulation tag. If you want to go to the next slide. And we've pretty much caught up to the present day. So we talked about this in space news earlier. So on Monday, phosphine was detected on Venus. I'll just run through this real quick again. So phosphine gas can be produced in a number of natural ways, as well as by life. The authors of the paper that discovered this couldn't find any explanation for how Venus can have phosphine on it, which means that there's some unknown chemical process that produces phosphine on Venus, or possibly life. So we'll look into it more.
All right. So yeah, that's it. We've now caught up to modern day. That's all of astronomy, or at least the big things in astronomy from 1600 to 2020. And now we're going to try to decide what the most important astronomical discovery was since Galileo. So the way we're going to do this is we're going to split everyone up into some breakout rooms. So basically you'll be a team with maybe 4 or 5 other people. And it's your team's job to decide what you think the most important discovery or development or technological achievement in astronomy was since Galileo, and then we're all going to come back together, and each team is going to present their opinion on what the most important discovery is, and just discuss it from there. Maybe debate back and forth for a while and see if we can come to a consensus in any way. So what we're going to do is we'll have one eBoard member in each breakout room with each team. And the eBoard members all have a Google Doc where we're going to write down once our team has decided a topic. So just to make sure we have some stuff to debate once we come back, no 2 teams are going to be allowed to do the same topic. So you might have to go with something other than what was your first choice, depending on which teams decide first. But I will get our breakout rooms all set up and we'll get that started in a minute or two.